Well, hello and welcome to another DevNation. We're here for another tech talk today. We have a great topic for you. We're going to basically talk about not only Kafka and Kubernetes and OpenShift and all that kind of awesome stuff, but we're going to show you the world of IoT and Internet of Things. Paulo today is one of our IoT experts, and he's going to talk to us about looking at the chat, and we're going to see Paulo get it started here.
Hi, Burr, and thank you very much for inviting me here. So let's start. Today, we are going to talk Apache Kafka in the hybrid IoT. So we are talking about how we can use Apache Kafka for IoT solution and how we can mix this kind of technology with some other traditional messaging technology. So how they can live together. So just a little bit on me. I am Paolo Patierno. I am principal software engineer in Red Hat. I am on the messaging and the IoT team, mostly working on the Apache Kafka side and, of course, on IoT. And I'm also committers on some different Eclipse Foundation projects like Hono, strictly related to the IoT, PAO, and even Vertex, related to some component as the Kafka client, NQTT client and server provided by the Vertex project. So let's start. Do you know what's about the IoT? When we talk about IoT, we talk about going from the sensors to the cloud in most of the solutions that we have, and then back to the devices, right? So we start from the sensor. The sensors provide us some raw data from the field, so they are able to getting information from the field. And starting from the sensor, we have to climb somehow this data information, knowledge, and wisdom pyramid, where we can try to get wisdom from the data that we have from the sensor. So we start from the bottom here, from the raw data. So we have the need for ingesting the data from the devices which are running in the field. And then we have to apply some sort of processing and analysis on data in order to get some information and then the knowledge from them. One time that we reach the cloud, so we have there some intelligence. Yeah?
Paulo, we need you to screen share. Great stuff, but we want to see what you're talking about.
Sorry, guys, you were right. Can you see my screen right now? So let's go quickly. I'm going to introduce how we can use Apache Kafka and in the IoT solution. So how we can use Apache Kafka in the IoT and how we can mix Apache Kafka with traditional messaging solution. Just a little bit from me. I am Paolo Patierno. I am a principal software engineer here in Red Hat. And as you can see, I am working on messaging and the IoT team. So as I said, we are talking about IoT, so how we can go from the sensors to the cloud and then back on the devices. So we start from the sensors. The sensors are on the field, on our devices, and we have to get some information from them. So we have the raw data that we need to ingest in our platform, and somehow we need to climb this kind of data information, knowledge, wisdom pyramid in order to reach the cloud and getting intelligence from the information that we have from the sensors. So we have to apply some processing and analysis on this data, right? The time that we reach the cloud and we have our IoT services running in the cloud and our intelligence there, we can control our device. So we need to come back to the devices using some sort of commands. So in order to control the actuators that we can have on the devices and driving what we have on the field. So we have two ways to interact in the IoT space: getting data from sensor and controlling the devices where the sensors lives. Then when we talk about IoT, and then when we talk about data from the sensor, we have to think about a huge amount of data to ingest in our system. And we have to think about that this data set is unbounded. So we don't know when the data will end because it's an unbounded data data set. And we can do on that some time of real-time analytics and getting some real-time reactions from this data. And somehow we also need to join this real-time information from the devices with static and historical data in order to enrich the data that we have from the sensor. So what we need is a kind of different type of processing. So instead of having what we know as the batch processing, we have a new kind of processing, which is called the stream processing. So what's about the stream processing? As you already said, is a kind of processing where you have to handle an unbounded data set, so an infinite data set. You have to work on the data as they arrive into the system, and you can kind of getting some information in terms of windows. So you can define a sort of time window where you can get some information from there. So you can define some boundaries for your data, but just as windows on the time. But what are the good parts that we can get from the stream processing for the IoT? First of all, the timing. When we talk about events and data from the sensor, we have different kind of times that we can get in the stream processing world. But the most important ones is the event time. So when the event is raised on the device, so when the data is get from the sensor and not the processing time, so the time that I'm going to process that event. Why this kind of event time is important? Because in that case, we can consider that sometimes the device can be offline, so any events happens on the device, some data is get from the sensor, but the device is not able to send the data to the cloud because it's offline. In that case, we can have on the stream processing side some events coming out of order, so after they were raised on the sensors, but thanks to some streams processing technology, we can handling this kind of scenario. So handling in the right way the events that come out of order. And we can also use the windowing, as I already mentioned. So we can say that in a specific time window, we are going to process and we have some outcome from there, as we will see during the demo. We have also the need for doing some state management. So we have to enrich the data that we have from the sensor with some static or historical data. And we can also, for example, with stream processing, joining different streams of data. So having streams coming from these different types of devices and then joining this data in one stream. The other interesting thing is about reprocessing, because we are ingesting this data, we are saving them, and we can think about to read the entire stream if we need to reprocessing the data that we got from the devices. And the other important point is about scalability, because we want to handle the stream processing even when we have tons of devices sending data and we have a burst of traffic, right? So what we have in the IoT space for the stream processing, we can focus on the right-hand side of this picture, where we need a platform for ingesting the data, and we need a sort of framework for doing the stream processing. So we have need to get two different platforms for doing IoT in the streaming world. But in order to do that, we can think about different projects, different solutions. So on one side, we can think about Apache Kafka. Apache Kafka is a real great system in order to ingest our data from the sensors. But at the same time, we can think about some other stream processing framework like Samza, Spark Streaming, Flink, which allow us to handle the data that we can ingest using Kafka. But think about that. It's really true that we need two different platforms, two different projects and technologies in order first to ingest the data from the sensor and then processing the data, doing real-time analytics on that. Well, it's not so true today because we have, other than Kafka, so other than thinking Kafka as the core parts, so the brokers and so on, we can think about the Kafka Streams API. So in the picture, you can see that we can just use one technology, which is Kafka, using the core part with the brokers for ingesting the data and the Kafka Streams API for handling this data coming from the devices and from the gateways in the edge. So just a little bit of few information about what is Kafka. Kafka was born like a publish-subscribe messaging system. But then, time by time, it becomes to be more well-known as a data streaming platform. This is why today we also have this kind of a Kafka Streams API for doing data streaming, because it's really good for data streaming. But at the end, Kafka is a commit log. Of course, it's distributed by nature, it's horizontally scalable, and it's fault tolerant. So it's a system that can handle in a high throughput with low latency. So these are all features that fit really well with the IoT world. But other than Kafka as an ingestion system, on the other side, we have this new component, which are the Streams API. And the Streams API is a stream processing framework, so a framework for doing stream processing, and as we can do, for example, with Spark Streaming. But it's just a Java library. So we can just use this Java library inside our application for doing stream processing. So using Streams API, and instead of something like Spark Streaming, for example, we can avoid to have another cluster, so the Spark cluster, in order to run our stream processing framework. We can do that in same cluster where we have our Kafka brokers, and using this Java library in order to do that. The streams are represented by topics, as you can see here on the right-hand side. And you can build your application making a sort of topology. So you can have one or more source processors. We are the node that are getting data from the input topic. Then you can have one or more stream processors in order to do the real stuff. So in your topology, you can do filter, you can do some map, so changing, for example, the content of the message. You can do joining with the other topics, and so on. And at the end of the topology, there is another node, which is the sync processor, writing this processed data into the output topic of our pipeline. And as we can see later in the demo, it's really simple writing to write a Streams API application. You can use a sort of high-level DSL in order to describe this operation in a fluent way, but you can also use a low-level processor API if you need some more complex processing. But after ingesting the data and then processing them, it comes to control the device, because we are just halfway, right? So we have to back to device in order to control the actuators that we have on them. So it happens that we have different needs compared to data ingestion. First of all, for example, we need something like a correlation between the command that we are sending and the result, the response that we are getting from the device, if the command was executed, if it went well, or there are some errors, and so on. We need to execute, for example, most of the time the command maybe just one time, so maybe we don't need to store the commands, because we don't need some histories from the command. But Other than that, so related to storing the command, we can say that sometimes we don't need storing because we want just to the device executing the command when the device is online. So we want our platform reaching the device with the command only if the device is online, and not storing the command somewhere and then having the device coming later in order to get the command. So maybe we have different needs sometimes. And one more important thing is that most of the embedded devices in the IoT space are really low power. So there are some more different, more focused, IoT focused protocols that fit better on embedded device like MQTT or AMQP and so on. So for this reason, we can, of course, using Kafka for ingesting and for real-time analytics on our data, but we can still use some traditional messaging technologies that provides all the features that I already listed before. So we can use some other kind of protocols, like, for example, one of them is AMQP 1.0, which provide us a way for handling not only a publish-subscribe pattern, but even a request reply, which is important in the command and control case. So we have a way for, with AMQP 1.0, we have a way for sending the command when the device is online, as I said, or even storing the command. So having an intermediary like a broker storing the command, but we can put on this command a time to leave information about having the command expiring. If the device, for example, which is offline, comes back online too late, and it's not the case to execute the command too late. So we want having the command expires after a long time the device is offline, right? And we can also check the status of the delivery or cancel it. And one of the other features from this protocol is also about filtering the message at the source if we need that. So as I already mentioned, and you can see better in this picture, we can have two different kind of ways for communication between the service in the cloud, which is controlling the device. So I can say the producer, and our devices as the consumer. One is having a direct communication through a router's network. So for example, using the QP dispatch router project, which provides an AMQP.1 router. And in that case, we have a sort of one-to-one contract between producer and consumer. So I know that the command reached the device because it's really online and it's starting to execute the command. On the other side, we can think about in a situation where we want to store the message, so we can go even through our router's network, but then the message, the command in this case, is stored in our broker, and then the consumer, so the device, will come back later in order to get the command for executing it. So in this case, we have two kind of contract between the producer and the broker, and then the broker and the consumer. So we have this intermediary in the middle, which is storing the commands for us. But as I said, we can also use a TTL on the command in order to avoid stale messages not executed on the consumer side. But how we can put all together? So mixing Kafka and this traditional messaging solution. First of all, we have to think that today, most of the devices are not connected directly to the cloud, but we put some logic to the edge, as we say in the fog. So we have some IoT gateways where the devices are connected, and then the gateway bridge the traffic from the devices to the cloud and the command to the device on the way back. The gateway are really useful because we need some protocol translation somehow, because our devices can connect with some other kind of protocols like Bluetooth, so BLE, ZigBee, or even using MQTT and so on. We can also reduce the workload to the cloud because we can do some processing on the gateway. We can have some real-time reaction on the edge, at the edge, and even handling a situation where there is no connection to the cloud, but we need the processing locally, and so we need some offline handling. Of course, thanks to the gateways, we also have more security for our data, and we can also reduce the price of having too many data flowing to the cloud if we are paying for the amount of data that we are transferring to the cloud. So how AMQP.1 can fit into the gateway instead of using, for example, a gateway connecting directly to the cloud using Kafka protocol? Well, first of all, as the Kafka protocol works, all the brokers need to be reachable from outside the cluster, and it needs that the gateway have to open different connections to these brokers, right? And somehow in the Kafka space, the request reply doesn't fit so well. This is the reason why Kafka mostly was born for publish subscribing in the messaging world and then coming as a data streaming platform. With AMQP 1.0 on the gateway, we can have a solution where the gateway just open one connection to our cloud solution, where we can use, for example, the QP dispatch router for handling connection, of course, from different gateways in order then to handle scalability and failures. But with just one connection, a gateway can use the AMQP.10 multiplexing features, where I can have different links inside the same connection, use it for sending the data from the gateway got from the devices, or using another link for sending the command to the device, right? So we can use this just one connection and multiplexing through the links. But let's see how it really works. So I'm going to show this demo where I have on the left-hand side an IoT gateway. It will be my laptop in this case. So I have the software running on the IoT gateway is deployed and developed using Node-RED, which is a platform for flow programming development. So I'm going to use a Texas Instrument sensor tag in order to have a real device sending temperature and humidity data using Bluetooth to my laptop. So in this Node-RED flow, I am going to use a node for getting data via Bluetooth, and then another node in order to send this information to OpenShift, where I'm running Kafka using an AMQP connection. So on the other side, we have an OpenShift cluster, a Kafka cluster deployed using the StreamZ project for doing that. The QP dispatch router in order to handle the connection from the gateway, just one gateway in this case, of course. And then I will have an Apache Kafka, an Apache Camel, application for bridging the data from AMQP to Kafka. Then all this data will be processed by the Streams API, and then we will have a sort of monitoring console for showing the data, and then coming back from the same console, sending commands to the gateway using AMQP through the QP dispatch router. So let me just show what we have running here in the cloud. So I will just stop to share the slide, but I'm going to show what I have on the OpenShift cluster. Here I have my StreamZ cluster operator that I use for deploying my Kafka cluster, and I have the other pods for the QP dispatch router, the Camel application, the streaming application running Streams API, and this control application which has this sort of console. This is a dashboard where I have on the left-hand side a consumer which is getting some information from a topic. In this demo, the devices are sending the temperature on an IoT temperature topic, and my Streams application is using a time window of 5 seconds. So every 5 seconds, it processes the max value of the temperatures, and then it sends the maximum value on this other topic, which is the IoT temperature max topic. So we should see here a picture about the value that we are getting from the device when I will connect my sensor tag later. On the right-hand side, we see an example of a simple commands dashboard where I am simulate a couple of commands in order to send these commands to the gateway on the other side. So talking about the gateway, here I have Node-RED running on my laptop. So I have this flow where this is the node related to the sensor tag. As you can see, it's discovering because my sensor tag is turned off right now. And when the data will be get from the sensor tag, they will be translated in an NQP message and will be sent to the cloud using this NQP sender node. At the same time, the message will be logged in the debug window on the right-hand side. This other part of the flow is related to receiving commands from the cloud. So we have an NQP receiver node, and every command that we are going to receive via NQP, we are just going to log it on the debug console. The interesting thing is that in Node-RED, you can define a sort of endpoint node, which is not visible in the flow. But in this case, I'm going to show you that I'm using just one endpoint node here, which is configured using a route, because from the OpenShift cluster, the entry point for the QP dispatch router is exposed using a route. So I'm using just this endpoint, and this is the same in the NQP receiver. So what I mean by that? I mean that these two nodes are going to use just one connection, what I said before, just one NQP connection through this endpoint, but they are going to use two different links. One for sending the data to the QP dispatch router and then ingesting them in Kafka, and another links for getting the command to the gateway. So just to show how it works, I'm going to stop sharing just for a few seconds in order to show you the device that I have in my hand. As you can see, this is a Texas Instruments sensor tag. Then I'm going to turn on this device, and we should see that the data will flow from the Node-RED flow to the cloud. So I'm sharing one more time, and I'm trying to turn on my device. So we should see at some point that sensor tag will be connected. It's connected right now. And we see on the debug console on the right-hand side that is sending data. So if we switch on the dashboard, now we see that the sensor tag is really sending some data. I have the device in my hand. It's sending the data. And now we can show how it's possible, instead of controlling the device, that I just turn off, to send some command to the gateway. So we can, for example, let me just clean the debug console. We can, for example, click on the command 1 button, command 2, and we should see here that the NQP receiver node has got some commands, these two commands from the control, and is logged that message just in the debug console. So this is the overall picture of the demo, where we are just using different messaging technologies in order to build a complete IoT solution. On one side, Kafka is really great for ingesting data, and thanks to the Kafka Streams API for doing some real-time analytics on that data. But maybe for handling some other kind of scenarios like the command and control, it's really useful using some other different kind of technology, like the traditional ones with some standards protocol like AMQP 1.0, even for handling the connection from the edge to the cloud in order to avoid more resources needed from the gateway for connecting to the cloud. So I hope that you enjoyed that, and if there are some questions for me.
There are some questions, and actually people were very excited about the TI sensor tag. So I've been chatting with people and showing them the link to the TI sensor tag. So that was a big win for us today. But one question here from Federico is, does StremZ have a component similar to MQTT proxy available in the Confluent distribution? So that actually is a very good question. Is you bridged the dispatch router, because that's not, Bluetooth to Qubit dispatch router needs a bridge, right, of some sort. And then was it MQTT or is it AMQP? And then, what about the MQTT proxy perhaps on Kafka?
Yeah, that's true. But the point that I made here is that, yeah, you can use an MQTT bridge as well, but you cannot use then the features that we have with the NQP, right, which is about multiplexing. So you need to connect using more connection in that case. But yeah, you can also use MQTT in this kind of scenario. That's right.
Okay. Yeah, and I think that was some people were interested in MQTT part. But I mentioned also the sensor tag is sold directly by Texas Instruments, so people can go there. I added the link to StremZ, so people knew where the Kafka was coming from. Oh, is there a link to your demo setup with maybe the YAMLs needed to deploy this to my OpenShift?
Yes, I will share my GitHub repo where you can have all the steps in order to reproduce all the deployment and having it working in 5 minutes or so.
Okay. And so the next question here, real life, a demo that's closer to real life. I actually say this demo is actually very close to real life because it has to do with the fact in the industrial IoT, you're going to be using the TI sensor tag to give you things like vibration data, heat data, light data. There's actually 10 different sensors in that tag, so you can actually have a lot of fun with it. So to get all kinds of actual sensing data going on. And so actually, I think the presentation actually is more of a real life architecture. Now, one thing, Paulo, you didn't show the gateway running in the field. Your gateway is running in the cloud. Is that true?
No, my gateway is running on my laptop, so it's running here on the field somehow, right?
Okay.
So my laptop is acting as a gateway, right? Yes.
Okay. And so that's actually where the gateway is occurring. So that's probably something people should understand better. If you could just briefly, and we're out of time, but just briefly walk through each from the tag to the X to the Y to the Z one more time so people understand the pieces of the architecture and the software involved.
So I can just show the slide for that. Let me show the screen. Yes. So can you see my screen, right?
Yes.
Okay, so on the left-hand side, I have the gateway, which is just my laptop in this case, and it's running Node-RED, so the flow that is able to get the Bluetooth data and then translate it in NQP. On the other side, I have an OpenShift cluster, which is running in the cloud, and I have used StreamZ for deploying Kafka. The Kafka Streams API for doing real-time analytics, the Qubit dispatch router as an ingestion point for the NQP connection from the gateway, Apache Camel for bridging NQP to Kafka, and then Vertex as the framework for having this web UI console for monitoring and controlling the device.
Okay. Well, thank you so much for that. We are out of time, unfortunately. There's still a few more questions in there. But, it's related to scaling and scaling of the architecture. And I was responding with the fact that, well, Kafka is really the part that's absorbing all this massive influx of data, and that's known to scale. Just to make that point, Kafka runs over 1 trillion transactions a day in LinkedIn. That's where it comes from, as an example. So most people feel that as long as you have the storage and the ability to deal with that volume, it scales no problem, right? And so you got to have enough CPU, enough computers, but it does scale no problem. Okay. Well, thank you all for your time. Paulo, fantastic stuff. I love the demonstration, but we are out of time. I apologize for that. You can always email me, though. Everyone here has my email address, and we can get questions routed to Paulo. And then we'll also, Paulo, when you get a chance, publish that link to some of your demo sources, and then people can email me for that as well.
Thank you very much, Bur.
Thank you.